Hello, pre-calculus. So we're ready for our last day of notes. So this is going to be 10.5, and we're going to be talking about statistical literacy. Now, the interesting thing about statistical literacy is really this doesn't have a lot of what you classically think of as math. This could easily be a section in a like an economics textbook or a social studies textbook. Anything like that, where you'd be looking at this. But basically what it comes down to is a lot of information is given to us through statistics, and we need to be able to understand what's actually being said and how those statistics are actually being determined, so we understand the reliability of those statistics. Just because it's a statistic doesn't mean it's necessarily reliable, and then of course we have to make judgments on what the implications are of that. So let's take a look at some literacy here in regard to knowing this. All right, so the first thing, we're going to define some terms so you can understand association. So what do we mean when we hear say something is associated or there's an association? It's the degree to which the data aligns to a mathematical model. So the closer it aligns to a particular model, the more association there is with that model. Now, one of the big problems that a lot of times people do is they assume association means causation. Just because something aligns well does not mean it causes it. Okay, so we have to be aware of that. It's like saying that, well, we notice that there's a definite association between people that buy peanut butter and people that buy jelly. Well, just because you buy peanut butter doesn't mean it causes you to buy jelly, but there is an association there. That would be like one simple example, but there's a lot of those that we could say are the case, where it's not necessarily causation in that case. So be aware of that. All right, let's go ahead. Let's take a look at another example of something, correlation. So when we talk about correlation, we say there's a strong correlation. Well, what does that mean? It's the degree to which the data aligns to a linear model. So association is the degree to which it aligns to any model, and correlation refers particularly to how well it aligns to a linear model. So that's an important distinction to make. Once again, correlation does not imply causation. Okay. Next thing, when we talk about correlation, we can talk about positive correlation. And when we talk about a linear model, a line, one of the main things that we need to know about that is its slope. So positive correlation means aligns to a positive linear model. In other words, a linear model with a positive slope. So in other words, as one of the variables is going up, the other one is also going up. And negative means it aligns to one with a negative slope, a negative linear model. So in other words, as one of the variables is increasing, the other is decreasing. Okay, next thing under correlation is to remember, correlation does not imply causation. And you could also put correlation or association. Neither one of those does not necessarily imply causation. Too often we think that because things are correlated, because they align well, that means one causes the other. And that's not necessarily the case. It oftentimes means there's a relationship between the two, but it might not even be that they're even really working together at all. It could just be that the same situations that's causing one is also causing the other. All right, next thing, finding random integers. One of the things you might be asked to do is find a random integer. So in other words, just pick a number at random. Well, the way that we do this is with our calculator. And we have something called a random integer feature. It's called randint. So if you look in your calculators, you will find that random integer feature. And you can get it in the catalog and type in R and go to it there. That's one of the main ways that you can get to it. In fact, that's really about the only way I know right offhand that you can get to it. There might be a way to get to it with the... I don't think there's a way to get to it with other options with your calculator that I'm aware of. But it's possible there is another way, but I'm not aware of it if there is. I guess you can get to it. You can get to it by number 5 in your menu. In your calculator. So if you hit menu, go to choice 5 under probability, and you'll see random integer. You can do random number, random integer. Random integer is choice 2. So you can go there and you can select that and you'll get this random integer. So what you do is you have to enter the first that you want to have your range between, the last, and then the number of integers. So for instance, if I want to do this, notice in my calculator here, I've got random int punched in there. So if I want a random integer between 1 and 10, I can go 1, comma, 10. And if I want just one of them, I can go ahead and just hit enter and it'll get me one of them. But if I want more than one, I can put an extra comma in here and ask for, say, 2 of them, and it'll give me 2 of them. Interestingly enough, it gave me 10 twice on that one. So that gives me any choice between 1 to 10, and I can do it that way. So that's random. We're generating a random integer. Another thing to be aware of is something called bias. We're really just defining a lot of things you need to be aware of with regard to statistics. Bias is basically something in the process that makes our conclusion invalid. It doesn't have to be something in a person's mind when we're talking statistically. It could be something in our formula or something in our methodology, the way that we gathered information, or things that that makes it invalid because it skews our results one way or the other. That would be the idea. So for instance, it would be like if you were trying to find out what the American people think, and you did a survey and you you only sampled people living in Minnesota. That would be, you would have a bias there. It would be biased towards people living in Minnesota, and it would not be valid for saying that's what America thinks. You'd have to be able to account. That's the example of something we would call bias. All right, if you are going to do something that is a true experiment, there are some requirements. So here are the requirements that are necessary if you're going to do a true experiment. First, you have to have a control. And basically what that control means is that you account for extraneous or non-test variables. In other words, you have something that can either keep them from being a factor, or you have something that accounts for them. In other words, a parallel thing going on that accounts for those extraneous or non-test variables so that you can rule them out from your sample. So you have to have a control. The second thing you have to do is you have to do randomization. You have to do something where you're not just like, so you can't go through the phone book and let's say pick every fourth name, because that's not randomized, it's based on the alphabet. You have to have something that truly randomizes your sampling. You have to be able to replicate it. You have to have replication. Okay, if you can just do it once, it doesn't become an experiment. Back in science classes, a lot of times they'll say it needs to be repeatable. Okay, so you need to have replication in it. Fourth thing, you need to have what's called blocking. Okay, what's blocking? Blocking is where you get an even random distribution. So it's known as, the term is called blocking. And so you've got to have a random distribution, but it also needs to be even. In other words, spread out over. So it's not enough just to go to Minnesota and randomly select people from Minnesota for your survey. If you want to know what the nation thinks, you have to get an even sampling across the nation, but it also has to be random. So both have to be in play. All right, let's look at some examples of how we're going to answer questions like this. Like I say, these really aren't what you'd think of as classical math type questions. So if we look in our books here, we're going to look at, this is section 10.5, and we're going to actually look at the problem set that's here. So the exercises. So if we look here at our first one, number 1, it says the following. It says well, first we're trying to do is say whether correlation is being used correctly. And we want to identify any statistical errors. So number 1 here, it says a newspaper article reports that a high correlation has been discovered between beauty and intelligence in college women. So there's a high correlation between those two. So we need to say whether it's being used correctly. So first what we're going to see is no, it's not being used correctly. And the real problem here deals with the subjectivity of particularly beauty. But these are not really, and so these are subjective, they're not quantifiable categories. how do you define beauty? There's no mathematical way to define beauty, so you really run into problems there. Correlation is a statistical measure and should not be used in this way. You have to actually be able to have defined numerical measures in order to use correlation. Okay, let's look at number 5. Number 5 says, Marcus says that the scatter plot at the right, and if you look in your book you can see it, shows a weak negative association between the x variable and the y variable. He then adds that the low correlation, and he gives a value there, r equal to negative 0.32, indicates that there is no significant mathematical relationship. So if we see those numbers are very spaced out there. So yes, this is being used correctly. We see that there is a slight negative correlation, but it is weak, okay? And so when it's this weak, we would have to say that, to the first there, that there is definitely a weak negative association. But to say no mathematical relationship is not necessarily true. Because if you take a look there, what you'll see is the pattern does look like a sine curve. So you have to be careful and say there's no valid mathematical relationship with a linear function. That's what correlation determines, is linear. But it does not mean there's no mathematical relationship at all. So we do need to be careful there. All right, let's look at number 7. So number 7, this one we're asked to tell whether the sampling strategy will result in a random sample. And if not, explain why it wouldn't be random. So for number 7, it says the HR director of a large firm wants to survey a random sample of the firm's 326 employees. She numbers the employees alphabetically and uses her daughter's calculator to choose 50 distinct numbers with the command random int, and then she gives the 326, the 1 to 326, 50. And so this does give it, because she used the random. So if she, by ordering them alphabetically, that makes her, she has to have something else that randomizes it. But since she does the random int, then the actual order they become selected at is random. So yes, it is. Now let's look at number 9. Number 9 says, to get a random sample of 50 Reno citizens for a political poll, a worker starts at the beginning of the telephone book. For each name in the book, he flips a fair coin. If it comes up heads, he calls the person. If it comes up tails, he moves on. Once he calls 50 people, he stops. Okay, this is not going to give a random sample. And while he's going through, it does randomize. If he went through the entire book, it would give a random sample, because each person has a random chance of being called or not. But since he only goes to his first 50, obviously anyone that's later in the alphabet wouldn't have a chance of being called at all, and all those people at the beginning have more of a chance. So the problem is it's biased towards those that have first in the alphabet. That's why it's not random. Number 13. Number 13 says, this one, we need to... we know that each one suffers from a form of bias. We want to identify the bias and tell a sample statistic might differ significantly from the population and suggest how the problem might have occurred. So for 13, it says, to gather feedback on his teaching, Professor Jones invites his students to visit his website and respond to a brief questionnaire. He is depressed to discover that 68% of those who respond are dissatisfied with his teaching. Okay, well, the bias here is that they have to choose to get on there and respond. So only the motivated are responding here. And what generally happens in these type of situations is people that are upset are usually much more motivated. People that are okay with things, they don't see any need to comment because they're fine with things. So that could very well be what's happening there. Okay, finally, number 19 and number 23. So here we are asked to identify which are experiments and which are observations. So 19 says a health class analyzes 30 cereal products available at a local food store, recording various nutritional data for the typical 1-cup serving of each. Okay, this is observation. Obviously, they're just going and looking. It's not an experiment. It's not necessarily repeatable. It's not necessarily have a control or anything like that. So that's an observation. Number 23 says members of the school swimming team Practice for 8 days under simulated race conditions wearing 3 different brands of swimsuits to see if any one of the brands leads to faster times. Well, this is repeatable. They are controlling the different things because they've got the different brands under the different conditions. They're timing everything. So this one is an experiment. Okay, homework 2 through 22 even. And hope things go well. And I probably won't have any more videos for you, but we will have Zoom times and we will have review assignments coming up to get you ready for the test. All right.